Okay, good morning from here in London and welcome to today's global webinar. Today's topic we'll be looking at improved machinery productivity while focusing on energy efficiency using system simulation. Delighted to have as your speaker today Mr. Lionel Broglia, who's the Business Development Manager for System Simulation here at Siemens PLM Software. I'll give a very brief bio and then we'll get things kicked off. As I said, Lionel is a Business Development Manager for the system simulation activities in various sectors, including industrial machinery. He is involved in multi-domain system simulations since 1999 and has had several positions such as technical sales, account manager, technical marketing, product manager, and now is the business development manager. Okay, so now that we have Lionel's bio over with, I'd like to hand over to your speaker today, Mr. Lionel Broglia.
So I will spend some time with you today to present you our solution for the machinery market. So my speech will be split in different parts. So I will briefly introduce some industry challenges for which we propose some solutions, and after I will spend most of the time on showing you the product with a live demo, and I will come back with some. I come back to the slides with some conclusion. So industry. So today we will focus more on industrial machineries, production machineries, but let's say that the approach can be used for any other industry like construction equipment, but also automotive and aerospace. But I will focus more my speech today on industrial machinery such as packaging or bottle filling or metal forming or textile machineries. Developing such machine requires finding the best compromise between different attributes. And typically they are productivity, accuracy, reliability, and efficiency. And industrial equipment companies must develop more and more innovative and multi-domain control system, including a lot of different kinds of actuators, electrical motors, but also hydraulic actuators, pneumatic system, and so on, to increase throughput, speed of production, quality, and so on. So indeed, the increase of the production rate should not affect the quality or the product accuracy, and at the same time also the reliability of the machine. That means that, and in addition, energy loss also is important to optimize. So that's why machine industry requires a strong new development techniques to accelerate the development time. And we can think also at optimization of in-operation performances. It says that it can be interesting when the machine is in operation to be able to maintain the performance as much as we can during the time. Reduce, for example, the number of operators or not rely on specific expertise of employees, and quickly also adapt the operation of the equipment for quality-specific product. So this whole bunch of challenges and industrial machinery manufacturers need to tackle now, and it implies an evolution of the development process. So in order to make sure that the machine under development offers good productivity and reliability, manufacturers have to optimize the sizing of the different subsystems, for example, the actuators or heating or cooling system and control system at the same time, according to the performance target. But at the same time, we need to make sure that we do not compromise reliability. For example, avoiding introducing vibration in the actuator structure coupling due to changes in the subsystem dynamics. So as a response to the worldwide race for innovation, machine builders have to reduce development time and associated cost as much as possible, particularly during the commissioning phase. So in other words, the time spent installing the machine and fine-tune the control system at the customer site has to be reduced as much as possible. This also applies for retrofit works or migration to new controller. Reducing manufacturing downtime is crucial to avoid major cut downs in production. Concerning energy efficiency, it's important to understand now that energy flow in energy consumption can be a differentiator from a machine to another one, and from a machine provider to another one. So understanding the energy flow in the machine in order to identify and minimize power losses in the system is very important. So a number of subsystem options have to be tested for each one of the machine's functions. This has to be done, compare their efficiency at system and component level, and doing this without simulation is much more complex and much more time consuming. Again, industrial machinery and process industries typically operate 24/7 for years. So to maximize profitability, it is important to maintain the expected throughput with the same quality level, with the same production cost. So, however, system aging is a reality, and maintenance has to be anticipated in order to limit production pause. So the machine or process control often has to be adapted due to change of production, different material, different required quality, and so on. So that's why performing in-operation assistance and predictive maintenance using a digital twin of the machine or the process opens the door to significant productivity gains. So on one hand, simulation allows to predict the future state of the equipment, so as to propose or apply modifications of the operating conditions. And on the other hand, the behavior of the digital twin can be compared to real values of the machine to detect deviation and discover malfunction, predict failures, and plan maintenance. All right, so how Siemens system simulation applies here? So Simcenter, as an introduction, is the Siemens software brand for addressing predictive engineering analytics. So Simcenter portfolio consists of solutions that span 3D simulation, mechanical and thermofluids, 1D simulation, and testing solutions. So it comprises a lot of well-known products such as StarCM+, Simcenter Amesim, and Simcenter TestLab. Additionally, it includes the new generation of 3D CAE solution called Simcenter 3D, expanding on the heritage of NX CAE, LMS Virtual Lab, NX Nastra, and LMS Samtech. So inside this product family, Simcenter Amesim and Simcenter System Synthesis. So Simcenter Amesim is an integrated, scalable system simulation platform which allows simulation engineers to virtually assess and optimize the mechatronic system's performance. It boosts overall system engineering productivity from the early development stages until the final performance validation and controls calibration. Simcenter System Synthesis helps simulation architects and project engineers dealing with the increasing amount of variance and configuration. The Simcenter System Synthesis is an integration environment that allows simulation architects and project engineers to create a heterogeneous system simulation architecture from available models and evaluate system performance. If we dig now a little bit further into Simcenter Amesim, what do we propose for industrial machinery manufacturer? So the first is to propose methodology to help optimize the sizing of multidisciplinary system, to simulate the transient behavior of multi-domain system like mechanical system, hydraulic system, fluid system, thermal system. The aim of this analysis is to estimate on a machine, for example, the cycle duration according to specific architecture, to check vibration if vibration are not introduced into the system, check if heating are not undesired heating are not introduced, and if how to cool down, and so on. So multi-physics simulation. So and at the same time, it's really important to simulate also the energy exchanges into the machine to track the losses, to optimize existing system and try to develop new energy efficient ones, and sometimes also to develop energy recovery systems. And globally to minimize the quantity of energy to accomplish a certain cycle. So the physics which are simulating within Simcenter Amesim are the following. So mechanical simulation, 1D, 2D, 3D. I will introduce you an example just after. We can also import flexible bodies. fluid system for sure, for many hydraulic or pneumatic actuations. So with pump or compressor, with valves, with cylinders, and so on. Electrical simulation as well, from motors, inverters, grid, and also thermal systems using gas, liquids, two-phase fluids, and being able to compute the heat exchange between different fluids and also solid parts. So the simulation model, again, for each physical model, we consider both the performance side and the energy consumption side. And our second offer is also to do validation and calibration of PLC programs. The aim here is to reduce the total time and cost of development of machineries and process, not only on the development of the mechanical part, let's say, but also on the control side. By using Simcenter and Amesim, the objective is to support PLC code validation thanks to the multi-domain model of the machine, and then couple the simulation model of the machine with the automation code. So on one end, so doing software in the loop, oops, sorry, I need to change the slide. So we have the possibility to do SIL, so we have the code of the controller, and we couple the emulated PLC with a simulation model of the system, or we can do also hardware in the loop, meaning you have the real controller, and we couple the real controller with the simulation model. And the objective is to evaluate the impact of the code modification on all the performances of the machine. And of course, we have different cases. The first one is when you are developing a new machine. That means that if you have the mechanical department developing using Simcenter and Amesim to size the different systems, subsystem of the machine, the same model can be used to support control people, automation people, to validate their control strategy. So benefit will be to reduce globally the time and cost of the development, because you can share this model between departments, and limit the commissioning phase on the real machine. But the same approach can be used also in case of retrofit of the machine. You want to change some specific part with some specific motors and even also controllers. When you are doing this, you need to stop production. And the problem is that the fact is that when you are putting together new components, you need to modify also the control code. When you start again, everything is okay. So the objective using simulation in that case is to reduce the pause of production and also reduce the risk for the machine and for the operators of the machine. All right. So after this first introduction, I will go directly to the software to show you several demos, which will hopefully show you the capability of the software. So what you have in front of you is a graphical interface of Amesim. Amesim is a simulation environment where users are creating models starting from blocks included into many physical libraries. As I said at the beginning, we have the possibility to simulate hydraulic systems. For example, you have here in front of you the hydraulic library and you will recognize easily a few components like pumps, like valves with different geometries, some pressure control valves or flow regulated valves, and so on. We have also mechanical systems like this powertrain library or this 3D mechanical library, and it will be this library I will use first to show you that Amesim can be used before having a CAD of your system. The interest is to do early sizing of multi-physics system. So that's why you can start creating your model without having the CAD. So here, first example, I would like to show you a simple double pendulum, just to show you how to create a model starting from scratch. So we will use here components included into the 3D mechanical library. So I will use this first element. We will support the the creation of the model and the automatic assembly of the different bodies. And so here we have different components. So we have a ground here. So I will simulate the ground connected here with a pivot junction. We have a first body, another pivot junction, and then a second body. So I put my first element on the screen, which is the ground. Then I will find into the junction the pivot junction. So you can connect directly the icon together. Then I will find a rigid body. I need to define the number of ports, the number of connection to my body. All right, in that case, I have two junction, and then I will just do a copy paste of these two elements to represent the second pendulum. And now I need to close my system, putting here a zero force source connected to the body. All right, so I have created now a visual model of the system that I want to simulate. All right, now I enter into the parameter mode. Okay, at the same time, there is an automatic animation created starting from the few information I put into the model. So typically, the first element here. You can see here the element of inertia and the item's location. So here what I will do is I will put the inertia, the body along the y-axis here. So I put, for example, the center of gravity at 1 meter, and the connection 1 will be at 2 meters, for example. Okay, 2 meters, sorry. All right, so you see visually it's changing. And for the second body, I can define the coordinates of this body relative to the first one or in an absolute mode. I will use relative mode, and I just do a copy paste of the parameter of the first body to the second body. All right. So now nothing more. I will go into the simulation mode and run the simulation. Here I will not apply any additional force except the impact of the gravity. So now I run the simulation, and I will have access to the visualization. Okay, and at the same time I can plot any information of the system. For example, I can plot the position of the center of gravity, or the position of the junctions, and so on. And so I have responses versus time. Okay. So first model to show you how to create a model starting from the library. But in case of a complex mechanical system, what you can do also is to create automatically a model starting from the CAD file. So let me show you. This. So I will open a new file, and in that case, I will use a tool which is this one, the CAD import. Right. So the CAD, I have a new graphical interface here, where I can select the CAD file I want to import. So obviously we have a lot of different format to possibility of import file. Sorry, just to find the step file in that case. So it will take a few seconds because we have a lot of body. So it's a CAD file related to a delta picker, And what I will do here, I will show you part of the process of creation of the model, not the full one, because we have only 45 minutes, and I don't want to bother you with all the part. So here we have the CAD file imported. All right. So with all the bodies here. So what I will do now is I activate the 1D modeling part, and what I will do is I will import two bodies. The first one will be this one, and the second one the long bar here. Okay, and of course these two bodies are connected here with the pivot, so we will create also the pivot. Okay, so first I select on this first bar. I click here, and then I define that the body, I define the primitive. So in that case, by default, you understand that it's a 3D mechanical, but typically I could generate a thermal model of this part, meaning that this bar will be reduced to a thermal mass with a certain thermal inertia, with some also thermal properties. But in that case, I want to generate a 3D mechanical model. All right. So it's a body, yeah, and how many connection I will have? Not two, but three. So the first connection will be, sorry, the first port will be this, the center of this cylinder. Okay. The second one will be the center of this other cylinder. The third one here. Oops, sorry. And that's it. So I have, as you can see here, I have the mass, the matrix of inertia, the position of the different, the position of the different ports. So all this information from the CAD will be transferred later on to the model. Okay. So I have selected the first body. I will now select the second one. In that case, it's again a body, in that case with two ports. Port number A is associated to, to this surface. Okay, so the center of the cylinder. And the second port will be the center of this cylinder. All right, okay. And now I will define a connection between my two elements. Okay, so I will create now a new connection. Automatically, he found two bodies. He found already the junction, but let me just verify if the automatic mode perform well. So in that case, you can see that I have the first body here with the three ports. So indeed, it's a port C, which is connected to the port A of the second bar. Okay? So they are connected. And now what I can do is I can already generate a model start with these only two elements. So I click now on sketch generation. All right. So you want to say it now? No. I confirm that I want to import a 3D mechanical model. Okay. I click on next, generate, and you can see behind the model being generated with the two bodies and the pivot junction in the middle. And if we go into the parameter mode, you will see that here all the information of inertia, position of the center of gravity of the different connection ports has been automatically imported from the data available inside the CAD. Okay. So when you do the complete process, you find you have globally this sketch with the different bodies connected with a moving part here. So what we have here, so the different elements, so the three times the same system connected to here the body which is moving, what we see here, 1, 2, and 3, and the body for which we want to move. All right. So now what I will do is, the interest now is to run a specific working cycle, and typically to define what should be the sizing of the electrical motor in order to perform a specific working cycle. So what we have here is a definition of the position of the center of gravity of the moving body here. And what we do is we define some control loops for which we some control loops in order so as to control the different motors here, the different position of the pivot junction, so as the center of gravity of the moving part reach the targeted value. Okay. So if I run the simulation, I will then compare the targeted center of gravity with the actual one, just to see if the control is performing well. So here you have some information on the calculation time. So you see that it's not completely real time, but it's also because I am not connected to a power supply, so my computer is also in a power energy saving mode. All right. At the same time, the model is computing. I can have access to the result, but now the simulation is finished. So here, what we have in red is the target position for the center of gravity in X, Y, and Z axis. And of course we can have access also to the animation of the system at the same time. Okay, so what you see here, 10% Y, 100%. Okay, so we are describing this working scenario. All right. So as we can see, the actual position is okay compared to the targeted one. And one interesting outputs of the model are the following. Typically, here we have still not connected the pivot junction to an electrical motor, but we have access to torque and velocity. And if I plot torque and velocity for the different pivot junctions, I have this output. So for each of the pivots, which are in the real system controlled by a motor, we have here target speed and torque of the different motors. So now the benefit of this mechanical model is to give me the target performance of the different motor to actuate the delta picker. So now you go in your and you verify in the different supplier catalogs, and I hope that Siemens catalog is also one you are looking into. And then you have selected your electrical motor, and then you can go into another level of details by using electrical motors and drive components of our library. So what we have here is a library of electromechanical components, and I will show you different level of models. Some are very functional. Typically, we will enter a maximum torque, maximum speed, maximum power as a constant or as data file. But we can go into the detail of the technology of the motor and the control itself. DC motor, synchronous machine, and so on. Induction machine, and so on. So first step is to use here a functional model of the motor. I will show you some example, some parameter here. And typically, what is also interesting inside Amesim is that you have the possibility to compute the energy consumption, the electrical consumption. But if you want to compute electrical consumption, we need to have also parameters of efficiency. So either you have these parameters of efficiency or you do not have, and we provide by default some maps you can start from. So the machine targets, which is coming from the results of the previous simulation, give me a machine. The machine requirement are the following: 10 Newton meters, maximum speed of 20 revolutions per minute, and maximum power of 10 watts. Okay. Here you have the efficiency of a reference machine, but a much bigger one. So in that case, if you want to use this efficiency map on your model, we need to resize, to rescale the energy consumption map on this machine. So typically, this point here, which is around 2000 RPM, in our case, it will be more around, let's say, 7 RPM, and the torque, let's say, the maximum torque here is 10 Newton meter. Here it was 34. Let's say that we put 5 Newton meter, for example. All right. So here I have my rescaled machine with the table of efficiency. So I am fine with this. I click on OK, and then I will use this value of efficiency for my simulation. Okay. So now, first step is to check that performance of the system is still okay. So again, I will run the simulation, and then we will check both performance and energy consumption. Okay, so at the same time as the visualization, the 3D animation, which is open. All right, so let me run now the simulation. Again, with this level of functional model for the motors, the calculation time will not increase so much. Yeah, something else to say is that the 3 electrical motors here are connected to the same power supply, so I will be able to plot the global electrical consumption of the system. All right. So I don't know exactly what's going on, because okay. So let me just go back. I apologize. Yeah, the real demo effect as usual. Okay, let me start with another component. That one, yeah. Okay. Sorry for the small delay. Anyway, you have an idea here of the complexity of the model that is being simulated. So with a number of explicit variables and implicit variables. But the user doesn't have to take care about the solver. What does it mean? It means that you just need to click on the run button, and automatically Amesim will select the best appropriate solver in order to solve the specific model he is running. And in fact, the simulation method. The integration method is automatically adapted all along the computation cycle. So that means that during the same simulation, you can have different time steps and different also integration methods. Okay, so now the simulation is started. So again, what you can plot is the following. So target of the position of the center of gravity. You see that controlling the Z and Y axis in a good way. Yeah, that's difficult also to control the X axis. Okay, but at the same time, you can again plot the different speed and torque of the different motors, and in addition, you have the electrical power for each of the motor. And in fact, for each of the motor, what you have access to the electrical power and also the power losses of the model, which are this power the power losses results from the efficiency of the machine. Okay. So for each motor, we have speed, torque, and electrical power consumption. So finally, we do have here in this graph the electrical power consumption of each of the motors and the total electrical power which is requested to actuate the complete delta picker. Okay, so it will allow you also to size correctly the power supply for your mechanical system. All right. So just an additional model I want to show you is a second level of electric machine. In that case, we have used not a functional model of a machine, but a DC a model of a machine using the technology. Here it's a direct current motor for which we do not enter functional parameters like torque, maximum speed, maximum power, but physical information like winding resistance or winding inductance, and so on. Okay, and then once we have the parameter of the machine, we have also functional models of the torque command. So how to translate the torque command into current command to apply to the electrical machine. So you see here that globally the parameters of the control is using the same parameter as the machine, obviously. Okay. So in that case, I have a speed command here. And we'll check. So I have a speed command here. So we increase RPM of the motor from 6,600 RPM to 8,400 RPM. And here we have the output of the system. Okay. So we have the transient aspect because the machine is starting at zero speed. So here the control model is computing the current, the target current for the armature and the field winding, and we directly apply this current to the machine. So we simplify, let's say, the power electronic part. What we can do also is to put a little bit more detail on the power electronics and use this information given by the controllers as target values. And what we have here is a control. What a real inverter is doing. We have some supply voltage, and so we control the quantity. We control the quantity of current through the power electronics in order to reach the desired current. So it's what is done here by modifying here the power electronic, the buck arm, the half buck arm component. We control the actual current of inside the motor, and we want this current to reach the target information. So we add additional transient into the system. The results will be a little bit different because we take into account additional transient. So for example here, if I compare the speed here of the inertia with the simplified model and the more advanced model, you can see here that there is a slightly difference into the transient. So, but this model will require additional information. And again, what you have is also the power consumption of the machine because you have the current inside the armature, and you have also the current inside the field current control the field control loop. Oops, sorry, not this one. That one. Okay. So now, if we come back to the slides so as to conclude my speech, and after I will be very happy to answer some of your questions. So conclusion to this seminar is that I hope that I have demonstrated today that the Simcenter Amesim, which is a system simulation solution from Siemens PLM, give you some benefits in case of development of industrial machines. First one is to perform the sizing of the different actuators of the machine. So today we concentrate mainly on an electromechanical system, but we could have simulating a hydraulic press, for example, and in that case we would have used hydraulic elements like pumps, motors, valves. So and as the output of the simulation means the sizing of these different elements. So one, sizing of different components of the machine, simulation of the transient behavior, what you have seen, and make sure that the quality, make sure that the cycle duration is the one that we expect, and then check also if we are not introducing vibration into the system. Validate and calibrate PLC programs can be also performed using the same model and connected with a more advanced control model being developed, for example, in an automation environment like Siemens TIA Portal. If you are if you are using Siemens Simatic S7 controllers, but other kind of environment like MATLAB Simulink, for example. And the simulation model allows also to track energy losses and energy consumption of the system, and try to find maybe to compare different components and check which one gives you a good transient answer, a good cycle duration, but at the same time minimize the energy consumption. All right. Thank you for your attention. If you want more details, of course, you can read on our website, also on the community. But again, I am open for any question.
So just for me to say thank you to Mr. Lionel Broglia, and of course thank you to you all for your time. With that, the session is closed.